From this lecture, we'll talk about solving this equation, the 1D second-order differential equation, with the so-called Dirichlet boundary condition. U0 is equal to A, U1 is equal to B, by the using the finite difference scheme that we have already studied. So recall that the D2U at xi that we just derived last time, this can be approximated by this is a h squared u x I minus 1 plus minus 2ui plus u xi plus 1, right? So this approximates u double prime. Why negative u double prime is equal to f instead of just working with u double prime is equal to f. There's some technicality that's outside of this course, but if you really hate negative u double prime, you can simply do your u double prime and treat your f as a negative of my f. All right. So we're going to stick with the negative u double prime. It will be clearer in a moment as to one reason why we're doing this. So that means the negative u double prime at xi, this can be approximated by h squared negative u of xi minus 1 plus 2ui minus uxi plus 1. All right, and this means that if we have a grid, as we were talking here, we have 0 to 1. Here we have x0, x1, all the way to xm plus 1. All right, xm plus 1. So here is xm. That means at xi, at a grid point xi, because we know negative u double prime is equal to f. On the other hand, negative u double prime can be approximated by that. So that means h squared here, negative u xi minus 1 plus 2u xi minus u xi plus 1. This is approximately equal to f at xi. Okay. So then the goal is to solve all these equations. Why all these equations? Because there are many of them, and then you can let your I to be equal to 1, 2, all the way to m. You would need at every location you will need a point to the left because you have xi minus 1, and you need a point to your right because you have xi plus 1. So we cannot really enforce it at x0 or at xm plus 1. That's why it starts with 1 and ends with m. Okay? So we basically, let's rewrite that. What we have is that we know now we're going to use a subscript to denote ui, to denote u of xi. U0, we know that's equal to A, and um plus 1, we know that's equal to B. It's given boundary condition. And for the rest, we have h squared negative ui minus 1 plus 2ui minus ui plus 1. This is equal to fi for I is equal to 1, 2, all the way to m. Okay? And the the next step is write this as a linear algebra equation, and because we know u0 and we know un plus 1 already, so our unknowns are u1, u2, um minus 1, um. Okay, and then you have a big m by m matrix. M by m matrix. This is equal to something. Okay, the right hand side. So when I is 1, so the fourth row corresponds to the fourth equation. So when I is 1, so when I is 1, this means that negative u0 plus 2u1 minus u2 divided by h squared is equal to f1, right? F1, and of course we only have unknowns that starting from u1. Only u1 and u2 are unknowns for this particular equation. So basically, we move u0 to the right hand side, which means 2u1 minus u2 divided by h squared is equal to f1 plus u0 divided by h squared. Okay, that should give us the first row. If all the equations have 1 over h squared, so we're going to put 1 over h squared in front of the matrix. And we need a 2 to hit u1, so it's a 2 here, and then we need a negative 1 to hit u2, okay? And right hand side is nothing but f1 plus u0 divided by h2. So that equation will give us the first row. Okay, first row. When I leave it empty, it means 0. So starting from the second row, we have the same structure. Right? We have this same structure. -1 to -1. So you can see that it will be -1 hitting u1 here, and 2 hitting u2, -1 hitting u3. This pattern continues toward the second from the last. We're going to get 2, -1, -1. All right, and that will be when I is equal to m minus 1. When I is equal to m, the same thing happens as the first node. You're going to get 2, and then you're going to get -1. All right, let me move this 91 a little bit. This is right on top of that 2. Okay, so that will be our matrix. The 2's, and then the -1's, -1's. So you have 2's on the main diagonal, -1's on the 2 sub-diagonals. And at x2, that's just f2, and all the way to fm minus 1, right? We don't need to move anything from that equation to the right hand side. The last one, what happens on the first one also happens to the last one. So we have fm, okay, plus h squared u0. It was u0 before, but we know u0 is a, right? So this is b. Okay, b. So there you go. That's our equation. Let me. So that's equation number 1. EQN number 1. EQN number 2, as we did already, that's just negative u1 plus 2u2 minus u3, right? This is equal to f2. This is equation number 2, right? So on and so forth. Towards the end, you have h squared. Right? We're going to ask the PE to be satisfied at xm. So that's negative u m minus 1 plus 2 un minus um plus 1 is equal to fm. Again, you move this guy to the right because that's equal to b. Okay, this brings us the last row. All right. So the next step is we do a little bit of analysis. This is so-called local truncation error. LTE, as we have done many times in last semester. So what do we do? Remember, we plug in the exact solution into the scheme. Okay, into the scheme. And call that tau I. So we're going to denote this matrix that we just assembled by a sup H. H means the little h, so it means it's discretization of a continuous operator. 1 over h squared, all right, that matrix, 2's on the main diagonal, negative 1's on the sub-diagonal, for total of m by m matrix. Okay, and we're going to denote the solution vector u sup h. That's that u1 to um vector. Okay, un vector. So the remember the is approximation to u. The components u sub I. Here, this u is a continuous function. To u, the exact solution to the equation negative u double prime is equal to f. Okay. Remember the local truncation error is that we plug in the exact solution into the scheme. Okay. Remember we always talk about that 2 by 2 table. One is that you have your UH, one is your U, and one is your scheme. The other one is your equation. Okay, if you plug in UH into your scheme, because you computed UH by your scheme, so you plug in UH into your scheme, that is satisfied exactly. That's exact. Okay, you plug in U into equation, that's also exact. Okay, and if you plug in U into your scheme, here is a local truncation error. All right, and we cannot really plug in UH into the equation, because the equation means it operates on in particular a differentiable function. Okay. So by exact, we mean the residual is 0, and by not exact, the LTE, that location, the residual, which is the left minus right, okay, is not 0 anymore. So the local truncation error is equal to the residual when you plug in the exact solution U into the scheme. So at node I, if we denote that by tau I, all right, so your tau I is going to be equal to is that AH UAU, right? You plug in U, AH U vector minus your right hand side f vector, right? This component I. So what this is you can go back to what before matrix, which is you had that h squared. Okay, you have a negative u xi minus 1 plus 2 u xi minus u xi plus 1. Right, that is equal to f. We enforce that to be equal to f and compute the UH. Now it's u, so it's not equal to f anymore. You subtract f at xi, you're going to get a residual. That's the residual is called the local truncation error, tau I. Okay, tau I. we do a little Taylor expansion. Tau I. All right, as we did many times, we expand uxi minus 1 and uxi plus 1 around xi. So you're going to get negative. This is u of xi. All right, the difference is minus h. So it's minus h u prime at xi, right? Plus h squared over 2 u double prime at xi, all right, minus h cubed over 6 u triple prime at xi, all right, plus 2uxi, right, minus another expansion with a u, so this uxi plus 1, this is u at xi, plus h now, u prime xi, plus h squared over 2, u double prime xi, right, plus h cubed over 6, u triple prime at xi. Right, this is divided by h squared, and then you minus f at xi. We didn't did the big O, so that was h squared. You have all the what we neglected, h to the fourth. Okay, h to the fourth. If you look at that, what you have is that these 2uxi and minus uxi would cancel. Okay, and hu prime and u prime would cancel, and clearly this would cancel with that. Okay, because negative becomes plus, and minus that. All right. So what you have is that this is equal to, you get h squared over 2 plus another h squared over 2. You get 1 h squared times u double prime at xi. This divided by h squared minus f xi plus the order h to the fourth divided by divided by h squared. You get order h squared. Okay, order h squared. Order h squared. So this just when we lost negative sign here. So that's negative u double prime xi minus f xi plus order h squared. The question is, what is this guy? This guy is actually equal to 0. The reason is because negative u double prime is equal to f, because f is the exact solution. So negative u double prime is equal to f at any location. Here u is the exact solution. Okay, so we know the local truncation error is actually order h squared. All right. Indeed, it's better for us to actually figure that out. What is that equal to? What is that equal to? In fact, the tau I here is that. So what we ignored from above is that what is you can see the pattern. So here is you have a negative, all right. You have h to the fourth divided by 24, and u to the fourth derivative at xi, all right, minus what we have from uxi plus 1. That's another h to the fourth over 24. U to the fourth derivative at xi, right? Then the h to the fifth term would cancel again, so we have h to the sixth left, and this guy divided by h squared plus h to the fifth cancel. We only have h to the sixth left. Okay, so this is how if we want to expand a bit more, we get this is actually equal to negative h squared over 12. We get h to the fourth, but you have h squared on the denominator. So that's negative h squared over 12, u to the fourth derivative at xi plus order h to the fourth. Okay? So that will be used later. We're not going to dig deeper into that. But for now, we need to know that tau I is of order h squared. Okay. So if we call tau, the vector tau to be of component tau 1, tau 2, and tau m, basically the value of the local truncation error at location xi as we did above. We know we have that the UH that we defined above is equal to F. F here means a vector, F vector is equal to F function evaluated at x1, F function evaluated at xm. Okay, so UH is a solution. So UH solves AH, UH is equal to F. And that's number one. Number two, we have that we just claim if we plug in U, the exact solution U vector, okay, and that's not equal to F. That minus F is equal to the tau vector we just did. The U arrow, this is the exact solution vector, which is U evaluated at x1, U evaluated at xm, and the U is again the exact solution. Okay. So from these two statements, from these two equations, we know that if we define the arrow, okay, the arrow E to be U minus UH, okay, U minus UH. So that's the difference between the exact solution and the approximate solution. That's what we care, what we eventually care. You get an approximation, you want to know how accurate it is. Without solving for the exact solution U, because usually you don't have access to the exact solution, but you want to have some description of your error, to quantify your error basically. And one observation we have is that if you plug in AH, if you multiply H to E, what is that? That is AH U minus UH, all right? And we know AHU, and then we know AHUH is F. So that's exactly equal to tau. Okay, so we use those two equations basically here. All right. Which means that the error is equal to the AH inverse times tau, the inverse matrix of AH times tau. All right, and that's a key equality. So by analyzing, which means that analyzing the local truncation error tau, we may have information about E. What we care is actually the error of your approximation, and we may, so for that to happen, for for us to conclude that we indeed have some information about the error, we need the notion of stability. Stability. Here's for mesh with size h. Okay, so we have the mesh already. The mesh is, remember, the mesh is at grid. If we mesh is at grid, okay, x0 xm plus 1 of size h. If AH inverse exists, right, so that matrix should be invertible. If AH inverse exists for H small enough, and there exists a constant C. By constant, we mean it is independent of H. So your H, you can use more elements, more grid points. Your H gets smaller, but this C does not change. Such that if you can find such constant, such that AH inverse matrix norm is less than C, right, then we say this scheme is stable. So what this means is that if we have stability, that means that the main above is actually certain. For sure, we have some information about E. Why? Because if you take the norm of both sides, the norm of E, this is equal to the norm of AH inverse tau, alright? The product, the norm of the product is less than the product of the norms. So this is less than AH inverse norm times tau norm. Okay, times tau norm. And we know it's stable, so AH inverse is less than C times tau norm. Alright? We use the stability, which means i.e. if the local truncation error tau is small, then the error E is also small. Moreover, if tau is of order h to the p, like what we just showed, p is 2, we show tau I is of order h squared, then the error converges with order h to the p as well, because E is less than C times tau, and tau is order h to p, and C has no h in it, so E is also h to the p. This is the typical notion in numerical analysis, which is consistency plus stability means convergence. If a scheme is stable and the scheme is consistent, then we know it's convergent. Consistent is a weaker requirement for what we just did, the order. It basically means if you have any order that is consistent, you don't need order 1, order 2, order 8. You just need order h to some positive number. This is a special case. Now, the question now is that is AH inverse less than C independent of H? All right, that's a key question. Once we prove that, we can show that we know that the scheme is stable. Then we know it converges. The scheme that we just derived converges. The approximate solution from the scheme converges to the exact solution with order 2. Okay, with order 2. Next, let us show that. So first of all, what do we mean by a norm? That's some little bit of linear algebra. What do we mean by a norm? 1B is a matrix. For matrix B, right? Here, the matrix norm is actually a so-called induced norm. I just spent a couple minutes on that. The induced norm So what that means is that it defines the matrix B to be the supremum over all V, such that if you apply B to some vector V, you get another vector. You divide the norm of that vector by the norm of V. So basically, this is the same as if I only restrict on those V, all right, and such that its V norm is 1. So I divide it by 1, so that is like not divided by anything, BV norm. So you apply B to the vector of unit length, and the resulting vector's norm, the largest possible such a norm, is equal to that's definition. This definition, okay? So it's really induced by the vector norm. E.g., if we define a vector norm V to be 2 norm, okay, 2 norm, which is what? Which is V norm is equal to square root of V1 squared plus V2 squared plus Vm squared, okay? So for this particular case, so whatever vector norm would have a corresponding induced matrix norm. For this particular case, the matrix norm turns out to be the maximum eigenvalue, the absolute value of the eigenvectors, eigenvalues of A, of B. Of course, now we'll talk about the inverse. Okay. Another thing to recall from linear algebra is that if lambda is a eigenvalue of B, then 1 over lambda is an eigenvalue of B inverse, right? So this means that for matrix B, the inverse of B, the norm is equal to 1 over the minimum eigenvalues of B. Okay, because you flip all of them, and the minimum eigenvalue becomes the largest. So this is the largest for B inverse, which is equal to its 2 norm. So this means to show the matrix above that our AH inverse norm is 2 norm is less than C, we need to study the eigenvalues of AH. We need to find its smallest eigenvalue in absolute value. Then if 1 over that is bounded, then we are good. Okay? We need to study the eigenvalues of AH. So what is AH? We remember AH is 1 over H squared, right? The guys with 2, 2, negative 1, negative 1, negative 1, negative 1. 2 on the main diagonal, negative 1 on the sub-diagonal. This is a matrix M by M. By eigenvalues, what we mean is that is AHV is equal to lambda V. Okay, lambda V. Lambda V. So AH times some V is like multiplying that V by a scalar. And the trick here is that the multiple is to do this, but this is what this means is that because AH is like negative U double prime, you think of negative U double prime is equal to some lambda U, right? What kind of U can satisfy that? They have a corresponding V. So for example, if you take some sine x, we are talking about the interval from 0 to 1, so we're going to multiply that by a pi, sine pi x. Okay, sine pi x. That would do it. In fact, you can multiply that by any n, any integer n. Then n can be 1, 2, all the way to m. And here we're from 0 to 1, and so this means that we can try, if we try ui, all right, or vi, the vector vi is equal to sine m pi x. What is x? X is ia. So think of here. Here is x0. Here is xm plus 1. Our h is 1 over m plus 1. So xi is equal to ih. Right? This x1 is 1h. Xi is ih. So vi is m pi times that xi, which is ih. All right, m pi ih. So then what do we have? That AHV is a vector, right? Is i's component is equal to, we knew that's equal to negative u I plus 1 plus 2 ui minus ui minus 1 divided by h squared. Okay. So plug those in, we have negative sine m pi I plus 1h plus 2 sine m pi ih minus sine m pi I minus 1h divided by h squared. That's easy if you remember some trivial trigonometric identities. So we have 2 sine m pi ih, alright? And then we had sine m pi ih, the same guy, plus m pi h. And here plus another sine, which is m pi ih minus m pi h. Okay, this is divided by h squared. Sine cosine, we know that's just equal to, sine plus sine, that's just equal to 2 sine m pi ih cosine m pi h. Okay? Sine a plus b plus sine a minus b is sine a 2 sine a cosine b divided by h squared. Okay? So what is this? We're going to factor out sine m pi h. Alright? So we have 2 minus 2 cosine m pi h divided by h squared. This whole thing times sine m pi ih. Well, we know what is sine m pi ih. Let's just rewrite this down. M pi h divided by h squared, that's coefficient, times that sine m pi h, that's just vi. Okay, that's just vi, because the vi, we tried that, so it's just vi. So what we have is that i's component is equal to some constant independent with I times vi. That's direct evidence that AH, that's the same, is actually equivalent to saying AHV vector is equal to 2 minus 2 cosine m pi h divided by h squared times v. Alright. So we already, because this n is changing, so we already have 2 minus 2 cosine m pi h divided by h squared. Alright, here m is from 1 to m. We already have m eigenvalues. Alright, m eigenvalues. And because h is 1 over m plus 1, right? 1 plus 1. So which means the n times h, right? M is from 1 to m. This is less than or equal to m over m plus 1, and n is from larger than or equal to 1 over m plus 1. Alright, in particular, they're all between 0 and 1. So m pi h is between 0 and 1, 0 and pi. M pi h is pi times nh. Between 0 and pi, we know cosine function is decreasing. Alright, so negative cosine is increasing. So which means that the 2 minus 2 cosine m pi h divided by h squared is increasing with respect to WRT, with respect to n. It's increasing. So again, we want to figure out the smallest, because we're talking about the inverse, right? So the smallest is, we take n to be 1. It's 2 minus 2 cosine pi h divided by h squared. Alright, h squared. Divided squared. Is this bounded? The question is this bounded? Is this bounded as h goes to 0 for the definition of stability, right? And the answer is yes, because we know we have expansion for cosine x, right? When x is small, this is 1 minus x squared over 2, right? Taylor series for x small. So 2 minus 2 cosine pi h divided by h squared. What is that? That converges to that's roughly equal to 2 minus 2 times 1 minus x, which is pi h, right? Pi h squared over 2 divided by h squared. So by 2 minus 2 cancel, 2 times that over 2, that becomes pi squared h squared over h squared, which is pi squared. Pi squared, okay? Pi squared. It's more than just that. It's because the cosine x, we are taking, in fact, cosine x is not only can cosine x be approximated by 1 minus x squared over 2, it's actually larger than that. In fact, cosine x is always larger than that, because cosine x is 1 minus x squared over 2 plus next guy is x to the 4th over 24, right? Minus so on and so forth by Taylor series. So it's larger than that. So negative cosine is smaller than that. So which means what we did above, 2 minus 2 cosine pi h over h squared is actually the negative sign. That changes the sign of larger than, the less than pi squared. Okay? So we bounded that. Which means can take the c in the stability argument as pi squared. I mean 1 over pi squared, because it's a smallest eigenvalue of AH.